Okay. So welcome back, everybody, to the SMU Physics Department Speaker Series for Spring 2021. And this is the final event of our academic year, which is dubbed the Spring Colloquium. And in a moment, I'm going to invite Professor Derdana Balakisheva to introduce today's distinguished speaker, Professor Pierre Ramond. But before we get started, I wanted to make some of the usual reminders here. So to our audience on Zoom, I just wanted to remind you that to ask a question during or after the talk, you just need to type the word speak in the chat window. We use that as a kind of speaker queue, and we'll get to you in the order in which those requests to speak arise. If you ask to speak during the presentation, we'll interrupt Professor Ramond at the next slide change boundary or thereabouts, okay? And you'll only be able to speak when called upon by a moderator, which I will serve as the moderator, so Derdana doesn't have to worry about that for the event. The other thing to know is this event is being recorded on Zoom and it's being simultaneously live streamed on YouTube. The YouTube live stream is non-interactive, but we have a number of participants on the live stream today. So to our about half dozen participants on YouTube today, welcome. Without further ado, I'm going to now hand things over to Professor Derdana Balakisheva to introduce today's distinguished speaker. Derdana?
Thank you very much. It's my honor to introduce Dr. Pierre Ramond. He is a distinguished professor of physics at the University of Florida and a director of the Institute for Fundamental Theory at University of Florida. He earned his PhD from my alma mater, Syracuse University, and has held a number of notable positions, including as a postdoctoral fellow at Fermilab, used to be called National Accelerator Laboratory, and a Millikan Senior Fellow at Caltech, a member of Institute of Advanced Study at Princeton University, Distinguished Simons Fellow at Kavli Institute for Theoretical Physics. He is extremely well known for initiating superstring theory, generalizing Paul Dirac's work on point-like particles into a context of string theory, and he led to the discovery of the two-dimensional supersymmetry and the set of stage of fully four-dimensional supersymmetric formulation. He is the single author of 3 physics textbooks, I have them all, on quantum field theory, physics beyond the standard model, the group theory. His research has won numerous prizes, too many to mention all, but mostly Oscar Klein Medal, Leitmeyer Prize, Danny Hyman Prize, and most recently in 2020, Dirac Medal that was issued at ICDP, also one of the schools I went to. We're honored to host him, our dearest Professor Ramond, today to speak on unfinished standard model. And I underline unfinished standard model.
Okay.
Very good.
Well, thank you very much. Now this distinguished professor has to learn how to share his slides. The unfinished standard model. Yes. Okay. Now, so what the talk basically, as I said, was pandemically inspired because it led me to, I don't know, to lend some historical perspective, and then talk about the standard model, talk about possible completions, and in particular, work in detail on the neutrino strategy for trying to understand more about the standard model, which is the type of work I'm interested in, but it will basically tell you more or less, oops, something, okay, all right. Okay, so this is what so now, we are, as I said earlier, into physics, which still lives in a shadow of a genius. And then Mark Twain is he's supposed to have said this thing: history does not repeat itself, but it sure rhymes. So maybe it's not such a bad idea to go back a little bit in time and see how our field got to be where it is. So in a Newton century, once people understood what Newton had done, their application to Newton's laws led them to understand a whole host of phenomena. No matter what they did, they applying Newton's laws just worked. Then, historically, towards the end of that century, electromagnetism came up, namely with the invention of the voltaic cell, that you could store it and you did not have to take your life in your hands to study it. And that led to new physics. And the new physics, of course, is embodied by Maxwell's equation, etc. That a century later. Oops, oh, okay, sorry. Okay, so now let's look about, oh no, I'm sorry. Look at Einstein's century. Well, Einstein's century, of course, there's quantum mechanics, there's general relativity, but for us particle physicists, there is the standard model. And then we are left here with something we have no idea what it is, namely, oops, what am I doing? You know, dark matter. Does dark matter, you know, what place does it have? We have no idea. All we know so far is that we have things we do not understand. We don't understand quantum mechanics, we know how to use it. We don't understand general relativity, we know how to use it. We think we understand the standard model. We have dark matter, we don't know what it is. So it's a time full of questions. The only question is, can any of these questions be answered within one's lifetime? Okay. So the one thing that is very important is the ubiquity of the vacuum. In a century, well, before, when Newton was but a child, Descartes' view of the vacuum was a bunch of vortices. Descartes was the big genius of the time, okay? But the vacuum then under Newton basically was full of nothing. There was, okay? And then with Einstein, we know that it's full of quanta, okay? All right. But now I would like to make a pitch for history repeating itself, which is the Brownian motion calculation. The Brownian motion calculation of Einstein and Smoluchowski, okay, basically linked a physical phenomenon, namely Brownian motion, to a fundamental insight using statistical mechanics, basically, okay? But the thing that happened that was wonderful, Avogadro's number came out. Okay, and Avogadro's number was just the purview of chemistry. And once this happened, that was a real game changer, because all the people who were doubting the kinetic theory and everything, which were many of them, suddenly understood that this was the real thing. Okay, and that is where I say that perhaps we have similar problems right now facing us. First problem we have is standard model vacuum. Now the standard model vacuum, we know that in order to make a standard model work, we have to get, there's an order parameter in it. And there's something, and out with this order parameter comes the Higgs particle, which is extremely light compared to what its quantum expectations are. And the question is that just a defect of the theory namely we could add more, like we could add supersymmetry, we could do all kinds of addenda to the theory, or maybe does it tell us that there is something wrong with our view of space-time in terms of the vacuum? That's an open question. And then, of course, not too long ago, cosmological constant, which was obviously zero from the theoretical standpoint, right, is there. And I think it's fantastic, because the fact that it is there, we don't understand. First of all, we're not totally sure whether or not it's a cosmological constant, but it looks like it. Its equation of state looks a lot like it. And I go back to this, to Mark Twain. Why? Because when the next genius, when she solves the cosmological constant, she gets the number of the cosmological constant, the physical number. In terms of a cookie theory of space-time, we will know that that cookie theory of space-time will actually be, probably has to be taken very seriously. So there's something wrong with our vision of the vacuum. We don't really know it. Sometimes it works, sometimes it doesn't, but somehow the standard model, the Higgs, the lightness of the Higgs is really a problem that nobody understands. And my field has gone to a standstill as a result of this. Okay? All right. So let me tell you in what ways tell you a few details about the standard model. Okay, so you know, it's a theory of strong weak electromagnetic force between chiral leptons and quarks. But it's a beautiful quantum field theory, but it is built on flat space-time, which is something we don't really know. You think of the flat space-time basically as a phenomenological description, okay? But built on that, it's like building a fantastic building on the swamp, you know, okay? And sometimes something doesn't work out. So we don't understand at all what flat space-time is. In fact, we don't understand what space is. Now, when I was a child, the standard model, the thing for a quantum field theory was that it had to be renormalizable. And the renormalizability of a field theory meant that yes, it blew up at infinity in very short distances, but if you put a cutoff, and the cutoff was so far away from the experiment that it didn't really matter. So if you have a logarithmic cutoff, and I was taught that basically quantum electrodynamics was good because it was renormalizable, although people like Dirac thought that it was the wrong theory, okay? And nowadays, the view of this model is exactly the Dirac view. It's an effective theory. It's just an effective theory, okay, with a neutral scalar particle, which happens to be much lighter than the cutoff energy. That's the thing we don't understand, okay? And the explanation of such a small mass awaits. And the question again is there supersymmetry would actually alleviate the problem somewhat, but does it really necessitate a rethinking of what space-time is? And that is, I say, way beyond my pay scale. But when in the middle of the pandemic, I start thinking about stuff, big stuff like this, those are the kind of questions that come up. However, from the point of view of working on things, it works very well. I mean, you can, for most things, you can disregard these things. Okay, but let's see. So now let's talk about the local symmetries. Well, local symmetries of the standard model, SU3 cross SU2 cross U1, they are global symmetries. They could be, which is baryon number minus lepton number. There could be a Peché-Quinn symmetry, we don't know. Okay, I say that because my colleague that's here at Florida is Pierre Sikivi, whose life depends on the axiom. Mm-hmm. And it has basically 3 chiral families, which survived 50 years of experimental tests. Okay, and the model has such broad shoulder that it accommodates but does not explain neutrino masses. In other words, you put an addendum, okay, and you can explain. But the important thing about the standard model, it does not challenge established principles. Okay, there is no direct challenges to the basic laws, as we know them. So that makes it very difficult because usually fundamental progress comes up when there is a paradox between something that works and something that the fact that it works implies that some cherished principle has to be dropped. Something has to be done. And that happens, of course, rarely. But I think this is only for the true genius, you know, who basically understand what it is. Now, let's look at standard model and general relativity. Now, the good news is that from a standard model's point of view, you ask yourself, where is the cutoff coming from? Because it's an effective theory with a cutoff deep in the ultraviolet. Well, general relativity probably offers such a cutoff. So in a certain sense, from the point of view of a particle physicist, general relativity is just gives you a time where you know that perhaps space-time will break down and something funny is going to happen. But there is something quite spectacular about the Standard Model, which is not very much mentioned, is that there's an absence of gravitational Carroll anomaly. The Standard Model has 0 anomalies connected with the chirality, which is quite remarkable because it could have been different, and we don't understand. So the Carroll universe, which is what the Standard Model explains, somehow is shielded from these anomalies, even including the gravitational anomaly. And the most remarkable thing, in order to cancel the Carroll anomaly, you require both Carroll leptons and quarks. In other words, they combine into this. So this is really the first time that leptons and quarks are unified in their ability to basically get rid of a Carroll anomaly. That means that the Standard Model is a shadow of something very deep, except we don't know what it is. Now, what about dark matter? Well, the sad thing about it right now is that the Standard Model, there's nothing in the Standard Model that requires dark matter for consistency. So dark matter could be there, it could be an add-on, but it doesn't challenge any principle. Okay, all right. But we do know that the Standard Model interacts with dark matter. Why? Because gravity certainly is susceptible to dark matter, okay? And then the Standard Model is susceptible to gravity, and therefore their amplitudes. And therefore, at some level, there will have to be interactions. That's quantum mechanics coming in. There is no choice, except we don't know. Okay? So we don't know yet what dark matter is. Is it just a bunch of new particles, like the axion or some supersymmetric thing, or is it a game changer? Is it something that really changes? You know, well, we don't know that yet. In other words, some people, is it on the left-hand side or the right-hand side of Einstein's equation, so to speak? Now, in comes a way, now the gods come in. So the Dirac's principle of mathematical beauty. Dirac talks about the bimodal exploration of nature. One, experiment and observation, and from Dirac's point of view, mathematical reasoning. And he talks about simplicity and beauty. And simplicity, for him, it's Newton's equation. Okay. The beauty for him is the special relativity. Okay. And I should tell you something very interesting, and from his point of view, you should always look for beautiful things, which of course is very weird for a physicist to say that. But then Dirac was certainly a weird physicist. Okay, and one of the things, for example, talking about a deep thought, talking about this, is that Newton's equations are simple, and the question that Dirac asked himself, if they're so simple, why is the universe so complicated? And then he says, well, it must be quantum fluctuations. Okay, and this remained in 1938. So this is the kind of little remark that the gods leave behind, and now of course it's well known. People use this all the time, but that was the complication came from the boundary conditions basically, which can vary. It's kind of remarkable. Now I think that simplicity and beauty will meet at the Standard Model cutoff. That will be the point where everything will go. Unfortunately, the Standard Model cutoff is not within the reach of experiment. And right now, I don't think anybody's smart enough to understand what's going on, and we need experiment. Okay? Now, a cruel thing about the Standard Model is that it's weakly coupled at the CERN scale. If you look at 10 to the minus 15 well, if you look at 100th of the proton, of the extent of the proton, for example, you find that basically all the couplings in the standard model are perturbative. And this is very cruel. This is a very cruel thing for theorists, because perturbative theorists can use perturbation theory, and they can use the renormalization. So they can use, so it gives a field of play to theorists to extrapolate, okay, using the equations to shorter distances, which is quite remarkable, okay? So you look at the intersection of gauge and Yukawa couplings in ultraviolet, you find that when you go in the ultraviolet, there is a renormalization group equation which tells you that the coupling of the Higgs potential that makes it go up as a function of field configuration decreases through the radiative corrections, unlike the Landau pole, by the way, which increases the coupling. And it can cause instability, and there's some sort of a Planck chimney that appears. Very, very bizarre thing, okay? But this is one of the things that people look at. So the bridge to shorter distances, there it is. We know there's a bridge. We know that theories can go there. We are looking for patterns, okay? All right, so the grand unification. So one way of going through this bridge, which people following the beautiful work of Patti and Salam, okay, was basically that there was a unification of the local symmetries through asymptotic freedom, and that there was a convergence in the ultraviolet of the various couplings, and that led people to look at the symmetries of the standard model and extend to SU5, SO10, E6, and other groups, okay, which had the consequence of barrier number violation, okay, because in a Patti-Salam way of looking at it, a lepton, the electron, was a fourth flavor of quarks. With that symmetry was broken, so there was, it preserved baryon minus lepton number, but basically lepton number was. But proton decay hasn't been seen, so that means that this introduces in those ways of doing things a cutoff in the ultraviolet. Okay. We could look at another way, the intersection of the B quark and the tau lepton mass going in the ultraviolet. The mass of the B quark, okay, is described as half the mass of the upsilon part, BB bar compound at threshold, okay? And experimentally, the mass of the B quark is about 3 times the mass of the tau lepton. Now, if you use but the B quark mass is renormalized by the strong, by QCD to an extent that is not met by the lepton, and you can define a new scale where MB equals M tau, because MB equals M tau is a special scale for the SU5 theory. So the factor of 3 from the renormalization group sets another ultraviolet scale, okay, which would mean that new particles would be required. But then there's something, because if you use SU5, you get proton decay, and that'll be much, much too fast. So again, we don't know what we do. Now this, I want to make a simple pitch before I turn to the neutrino. Discovering proton decay. Well, if we discover proton decay, that's a direct bridge to Planck scale physics. So you don't have to increase the energy. You use Avogadro's number, lots of Avogadro's number to get to find proton decay. The present lifetime of the proton, which in the E plus pi naught channel, is 10 to the 35 years that Super Kamiokande has. Now, the near future, next 10 years, say, it will be increased to 10 to the 36 years with something called hyper K, which is more of the same. In the meantime, what do people like me do? Well, we look now for a bridge to the mystery of neutrino masses. Okay? Why neutrinos are massive and why are they so light? This is a very, it's not a very stable bridge yet because we don't know what's going on. So now the rest of the talk will be to talk about neutrinos. So the first thing about a neutrino, it was not born from experiment directly. It was born in the mind of a theorist. Okay, which means that it was not believed by experimentalists for a long time. Okay, it was coming from the south, and you guys are in the south too. It was the only elementary particle detected south of the Mason-Dixon line at the Hanford reactor in the Georgia-South Carolina border. Okay? And it was those were the original particles. And when they were followed in retrospect, they always brought new physics with them, in particular, chiral symmetry breaking. So it has been a rewarding research area. And now I want you to meet a few of the rewardees. Well, no less than Enrico Fermi, Wolfgang Pauli, Leon Lederman, Mel Schwartz, and Jack Steinberger, who passed away very recently. Okay, all right. But there were more. There was Fred Reines, Ray Davis, Mahiko Koshiba, Kajita, and now those two in color, they're still alive. Okay, so Kajita and McDonald were the last two. But there's another thing about neutrinos. There's something I call the Neutrino Hall of Fame. Okay, these are people who basically made fundamental contributions, but somehow died too soon or were not understood at the time. One, of course, is Majorana. Okay. The other one is Bruno Pontecorvo, and is Maurice Goldhaber. And if you teach a course in experimental physics, Goldhaber's measurement of the spin of the neutrino is probably one of the great gems of experimental physics through resonance scattering. I mean, it's just one of these incredible things. Then we got Sakata, another great genius. Bacall, who died too soon. Lincoln Wolfenstein. Those have also died too soon. So let's go to the letter. And I think this is interesting because of sociology. So the famous letter of Pauli, and he says, "Dear radioactive ladies and gentlemen, blah, blah, blah," and he tells, you don't have to read the whole thing, you can read it later on. You have a desperate remedy to save the exchange theorem, which was the Pauli exclusion principle, and the fact that, and then there was another problem, the energy theorem. Okay, and he said there could exist in nuclei electrically neutral particles with spin 1/2 and do not travel with the speed of light. So I want you to know this because when you look at the end of the the summary of it all, it's supposed to be very clear. It was not. And he said, "I do not feel secure enough to publish anything about this idea." Okay, but only those who wager can win. And then he says, "Unfortunately, I cannot appear in Tübingen because I'm indispensable here on account of the ball, etc." Wolfgang Pauli was a strange person, but you see what happened in his mind? The idea of a new particle, okay, which explains two things, was even that he did not write it down. Because probably inventing a new particle to explain phenomena was just not a macho thing to do, because the macho thing to do was to explain everything with what you had. Very different from today, whenever you have something new, you invent an infinite number of particles. And within a year, Pauli was analysis with Carl Jung, that's true. So Pauli's two problems, the Pauli exclusion principle, which was the following. In 1930, there had been very good measurements of Raman scattering on the nitrogen nucleus. And the nitrogen nucleus, this is before Chadwick, was made up of, we knew how much it weighed. So it had 14 protons and 7 electrons because we knew its chemistry had 7 electrons. Okay? So somehow there had to be something different, but that is a boson, as the line intensities are different from bosons and fermions. Okay, and then the second part. So this was a problem that people were worried about. The second part was the continuous energy spectrum of the beta decay electron. Okay, and those were the two problems. Well, so he calls it X, and therefore now we have the so he looks at the, he called it little neutron, by the way, yeah, little neutron, or neutron. I think he called it neutron by itself. Nitrogen nucleus, 14 proton per 7 electron plus X, and then he added the X in here, and that was it. Now, 1931, Chadwick neutron solved the nitrogen problem because basically the nitrogen nucleus, the atomic weight of 14 is actually 7 proton and 7 neutrons, so we know it's back to the way it is. And the little neutron remains. And in 1939, only 1939, says that Pauli's particle is not in the nucleus, it is created and emitted during beta emission. It took 26 years to find it, okay? And that was found by, oh, let me see, what am I going to do? Hold on. Okay, no. All right, that was done by Clyde Cowan and Fred Reines. Longevity. So first thing about neutrino physics, you need to live long. So you have to have a certain longevity for neutrinos. Now, the Pontecorvo brothers, next. So Bruno is the physicist, Guido is the biologist, and Gillo is the movie guy. Okay. He's the one who wrote the Battle of Algiers, and 1945, Bruno proposed a ways to detect neutrinos, which you hit neutrinos with chlorine, you get argon and you get electron. Fermi thought it was not practical because at that time, everybody went to Fermi to double check because Fermi was the guru of the time. Okay? But Pontecorvo never published. And the only time I met Pontecorvo, he regretted this very much, and he had reprints made of his Chalk River preprint. But Ray Davis uses it to count neutrinos from the sun. Okay? At the home state gold mine in Lead, South Dakota, pronounced Lead, which is now the site of Dune, the Dune detector, the Sanford Dune detector. And what happened, he assembled a bunch of graduate students and he took out the argon, okay? Because the argon that was produced was radioactive, lived only about a month. And therefore, if you did it quickly enough, you could count the argon. And if you are a certain number of argon, that would tell you how many neutrino hits there were. Okay, and Davis finds 1/3 of expected rate, there it is. In 87 comes the supernova, and the underground proton detectors that were being built just become basically neutrino detectors because a train of neutrinos was found. Okay. Then comes Super K, all right? And now Super K is a lot of material buried inside a mine, except the mine is that basically you drive to the mine horizontally because the mine is under a giant mountain and you drive into the mountain, okay? And those neutrinos come from cosmic rays and also from the sun, okay? And there it is. So from cosmic rays, you would find the decay products when the cosmic rays hit the atmosphere. You would find a certain ratio of muon to electron neutrino, where you find more or less the same, and you have the number. So you have different types of things. You have neutrinos that come through the Earth onto the detectors from neutrinos that come from above. And you expected something, you expect equal number, and you find, okay. And of course, the reason is that these guys were traveling different distances. Therefore, there was different oscillation. And then there was a zenith angle dependence. So they discovered a two-flavor oscillation. And the thing that was remarkable was that the angle that appeared in that oscillation was about 45 degrees. In the process, they confirmed the deficit of electron neutrinos that Devised form. And therefore, since they oscillate, that means oscillating from one to the other, that means you can distinguish one to the other. So you have to give them a label. And the only label that was available was basically their mass. Because, you know, in quantum mechanics, once you have a label, the label is a dynamical thing. Okay. So next come another guy, the snow detector, which now this is under a mine in Canada. And you look at deuterium, you look at dissociation by neutrinos, okay. All right? And you look at neutrino electron elastic scattering, and sure enough, electron neutrinos oscillate, the electron neutrino deficit is confirmed, the solar electron neutrino flux is confirmed. The angle is not as large as the other one for this, but it is the same, and the count of it counts neutrino flavors, and the late John Bacall, who basically did not live long enough to be rewarded for this, basically it was confirmed. Okay, and then the last mixing angle, okay, was basically the so-called reactor angle between the three neutrinos. Mm-hmm. And it was first discovered, hinted at by a reactor at the border between France and Belgium. And then, but it was really, with accuracy, it was the first Chinese experiment where basically it really measured the angle with a great deal of accuracy. And then the Korean detector Reno found it as well. And what it does is that basically there are neutrinos produced in reactors, et cetera, I mean, they are. The question is that you get reactor mixing angles, you have an L/E dependence, but in that case, the reactor angle is 8.5 degrees. Okay, so what you have is a remarkable thing, that basically you have the three mixing angle in a neutrino sector. One of them is of the, you know, it's kind of reminiscent of the quark mixing angles. You know, the quark mixing angles, the largest one is the Cabibbo angle, which is about 12 degrees. Okay? But the other two are very large. So something is happening. We don't know what. Okay. All right. So a little bit of theory. And so the question is, why are neutrinos so light? Well, let me remind you a little bit about the neutrinos. I guess we're running out of time. So the three neutrinos occur as basically doublets, one for the electron, one for the muon, one for the tau. They all have a third component of this weak isospin under which they are doublet, which is +1/2, that's the upper component. You could form for them a Majorana mass, which is neutrino-neutrino, but this has the weak isospin of, because this each neutrino has weak isospin 1/2, and as everybody knows, when you put two 1/2 together, you get either 1 or 0 for the total spin, but the statistics work here that you get 1. But if you give a lepton number to the neutrinos, you get 2. That would be one kind of mass. But it gets more complicated because you could add a right-handed neutrinos. Like, for example, the electron, there's a left-handed neutrino. You see the electron that is in a doublet here, that's a left-handed electron. But there is a right-handed electron. So you can add a right-handed neutrino, which has weak isospin equal to 0, just like the right-handed electron has also isospin weak equal to 0. And then you could form what is known as a Dirac mass, but it has very different quantum numbers. It does not violate a lepton number, but it violates the weak by 1/2 unit. And now comes the magic of this. Dirac and Majorana unite, okay, to provide an explanation as to why the neutrinos are so light. And the basic thing is what Murray Gell-Mann called the stupid little matrix. basically what it is that if you take, what happens, you look at a Majorana mass, and these guys are Dirac masses, and you don't put the delta I which equals 1. So in other words, okay, you don't put any Majorana mass in there, except for a very heavy one, for the right-handed neutrinos. And this guy here has basically an eigenvalue M, which is, you see these two matrix. When you look at the trace of this is M, but the determinant is small m squared. So that means that one mass is like capital M, if M is much larger. And the small mass, the other mass, is reduced by m squared over m. So it's reduced by the scale of the electroweak interaction by this unknown scale. And that is called the seesaw mechanism. Okay? Where basically by uniting all of this stuff, you get a very small suppression mechanism. Okay, so that is probably very important, and that the mass ratio is just the mass. So basically, I think what happens is that there is a suppression mechanism that comes from the existence of a new mass scale we know nothing about. Okay, and that is really the as they would say nowadays, the takeaway. Okay, all right. So if you try to explain all of this stuff, this suppression in the most sophisticated way, there is a limit on the mass of the neutrinos, which is provided by the Planck survey. And this stands for milli-electron volts. Okay. And that which corresponds in this stuff to about a scale of 10 to the 16 GeV. Okay. Now, what is interesting is that is the scale at which proton decay could become important. So there is a coincidence that perhaps the scale that appears in a neutrino physics may actually have something to do with a scale close to Planck's scale. And this is the dream that particle physicists are living with. Okay? Now let us go back and look at this neutrino mixing. The name of the lepton mixing matrix is called PMNS. P is Pontecorvo, Maki, Nakagawa, and Sakata. The three Japanese. Pontecorvo, with his reactions, it was more like neutrino, anti-neutrino oscillations, whereas all of those that have been observed today are neutrino, one flavor of neutrino to another flavor of neutrino. But MNS were under the Sakata, basically, once they knew there were two types of neutrinos, they started talking about mixing. But okay, and the question is that this object, UPMNS, which is measured, where those angles are measured, in terms of when you look at from a theory standpoint, it's made up of two parts. Two unitary matrices, or nearly unitary. One that comes from new physics we know nothing about, and one that comes electroweak physics, okay, the delta equals 0. So it means that naively, the experimental value of the angles could be basically a small component, because the angles in the quark mixing angle are all very small. So the black one would be small, and then there will be a new angle. So in this view, the two larger neutrino mixing matrix would be a characteristic of the new physics. And from my point of view, again, when I learned chemistry, large angles meant crystals. Large angles meant crystal faces. You measured angles between crystal faces, etc. Okay, so perhaps there is some sort of structure there, but nobody knows. I mean, I have ideas, of course, but I will not be believed, rightfully so, because it's not right. So let me show you what the present values are. It's like that, okay? And okay, so you see this guy here is small. These guys are, this is what we know, okay? All right. Now, so the quark mixing matrix, I was into bridges, okay? So the quark mixing matrix is a beautiful matrix, which has been measured to, but it is the mixing between up quarks and down quarks. Okay, that is the one. And so we know both sides of the bridge here. Okay. All right. The largest angle there is basically the Cabibbo angle, which I say is about 12 degrees. Now the lepton mixing matrix is that stuff. We don't know what the heck it is on the other side. Okay, and so this Pontecorvo, Maki, Nakagawa, and Sakata. Okay, yeah. By the way, Pontecorvo's brother, the Guido, if any of you remember the movie The Battle of Algiers, which was a very famous movie at some point, got an Oscar, etc. He's the director of that movie. And yeah, so he was a talented family, and the older brother was a biologist, well known actually. Now, so that is truly a bridge to the unknown. So that goes again, that is the kind of, and the good thing that happens, okay, is that now, since we have the unknown, what else can we do with it? Well, the first thing is that the large angles offer hope to explain the baryon asymmetry. Now, in the cosmology, okay, the conventional cosmology is that the universe started being symmetric, matter, antimatter, symmetric. And that the asymmetry that we see today has developed because of various mechanisms. And one which basically some were proposed, but so far nothing has really been understood. One is that we know that in this case, there is a lepton number, this is the total lepton number. There's a phase which experiments tell you is non-zero. This, by the way, is a convention that the particle data group uses. And then there are two Majorana CP violating phases, which we don't know. These two experiments are going to be, Dune and hyper K, okay? And then this neutrino-less double beta decay experiment, which will be, maybe the graduate students will see it, but I will not see them. Okay, there will be. So now the question is, theoretical challenge, and this is the last thing. Now, the model that people are playing with is saying that we should think of the mixing angles for the leptons as being beautiful, Dirac's view. Actually, that matrix actually was proposed by an experimentalist called Perkins. So there I'm defending myself because it's an experimentalist. Okay, and then the noise on this. Okay, so you will have the standard model side will not contribute to that, but it will contribute to filling this zero. Okay, so there will be a Majorana crystal at the cutoff. So is it simple or beautiful? We don't know the answer to that. So, okay. So I think I've filled your head. So one way of finishing a talk like this is that, I kind of pointed you to various directions of this, okay? But all of them are question marks. And the thing that is interesting, which I did not mention too much, is that some experiments right now are going to tell us something about the amount of this angle, for example, is going to be measured much more carefully. Right now, I mean, there is by the Japanese and perhaps Dune, we'll see. Okay, so the idea that Dirac simple and beautiful, maybe there is the neutrinos are trying to tell us there's something fantastic awaiting us, except we don't know what it is. So now let's turn to practical uses of neutrinos. First use, you don't need to build temples to the sun. Okay? Because we know where the sun is at all times. You see, in the old days, people used to build these things to make sure that the sun would rise again. because, from the beginning, the sun disappears and you never know. So the priesthood became very, very busy, making sure that, by building this, the sun would deign to reappear. But now, physics has taken the magic out of this. The neutrinos appear everywhere. So this is kind of a useless thing, but let me finish with neutrino chronology. So the revelation of the neutrinos, 1930, the detection, 1956, which is 2 times 13 years later, oscillations with a degree of certainty, this was the talk in 1998, okay, is 4 times 10 to the 7 years later, okay? And therefore, as is my old habit as a string theorist, I look at the pattern and I say, well, maybe I should generalize this for the next big experiment. In the big experiment, I see 2 to the first, 0 to the first, second, and third, and then the next prime number is 19. Therefore, that will be revealed in 2052. In the meantime, enjoy the starry nights. Okay, thank you very much.
Okay, no, thank you very much, Pierre. And since Zoom is so bad at applause, let's try to give you a little bit of applause here at the end.
Thank you.
All right. So we've come to the time when we can open up now for questions. And I see we already have one question from Pavel Nadolsky. So Pavel, let me go ahead and get you unmuted. Okay, you should be able to unmute. Leave yourself unmuted until you're satisfied with the answer, okay?
Hi, Pierre. Thank you so much for the wonderful talk.
Yeah, hi.
So I wanted to ask you, in your opinion, are there viable mechanisms of electroweak symmetry breaking that do not involve Majorana neutrinos? So in other words, are Majorana neutrinos necessary for breaking electroweak symmetry?
No.
No.
I don't think so. No, the order parameter of the electroweak symmetry is, well, it depends. For example, if you want to, you could forget about all this stuff and just look at the Majorana mass for a neutrino. Then you need an order parameter that is transformed as an iso triplet, not an iso doublet. The order parameter of the standard model is an iso doublet. Mm-hmm. But if you put an iso triplet by hand, okay, then you will introduce a Majorana mass. Mm-hmm. by its coupling. Okay. But the problem, now this would be a heaven for experimentalists, because once you do this, the Higgs guys that come, in other words, the guys that come with this Higgs triplet, one of them will have a double electric charge.
Okay.
So that's a paradise for experimentalists. Because then, something with charge 2 would be a thing. But then you have to explain basically why is the mass of a neutrino so small.
Mm-hmm. Okay.
Now Majorana masses are necessary to explain baryon asymmetry through leptogenesis. I did not have time to go into this, but it is really necessary, as is proton decay. Sakharov's way of talking about proton decay, which is baryon number violation. Well, that's one. But you see, in a standard model, B minus cell is left invariant. So if S is broken, then B is broken because B minus cell is invariant.
Okay.
So that is called leptogenesis that comes from that direction. Okay.
Mm-hmm. Mm-hmm. Okay. Thank you.
You're welcome.
Okay, great. Yeah, no, thank you, Pavel. Our next question comes from Tom Cohen, and you should be able to unmute Tom again. Leave yourself unmuted until you're satisfied with the answer.
Yeah, I have a kind of provocative question. In the run-up to the LHC, I heard infinite seminars where the statement was made at 1 TeV scale, unitarity is violated. New physics is guaranteed to pop up. What's wrong with that statement?
Well, well, there are new particles coming in, and they did come in, and there is a Higgs particle. There is, all these things are fine. The only problem that's not fine is that the mass of the Higgs is measured very accurately. In fact, some people have done it, and but there is nothing wrong. It's a quantum field theory, so it's okay. Unitarity is eventually violated, but not at that scale.
Yeah, but who was surprised that the Higgs was found? I mean, yes,
nobody was surprised that Higgs was found. But I will tell you that there used to be a time when the Department of Energy and the particle data group was actually handing out one sheet poster on the Standard Model, okay? Right? If you look at that, there is no mention of the Higgs. Okay, and the reason is because even though people like Steve Weinberg and others, of course, thought the Higgs was there, and certainly François Angler, and basically a lot of people thought there would be some strong coupling or something, that they, et cetera, okay, that there was no Higgs, okay, but the Higgs is there, and so for some reason, even in the 1990s, there were posters, there were official views where the Higgs, there was a whole community of physicists who thought that there was technicolor, that you got basically to have strong coupling, more strong coupling stuff. And by golly, I mean, totally amazing. As we go deep now, we learn that the couplings are getting weaker, not stronger. I mean, that of course is the magic of asymptotic freedom, okay, which people did not think about before. So the existence of the Higgs is there, it's perfectly okay. Except, why the heck is it at that mass? And what people thought is that if you added supersymmetric particles within a given mass range, you will explain why the Higgs would be light. Well, so the second part of the argument is there. The Higgs is relatively light, okay? But the first part of the argument, there's no trace of supersymmetric particles in that mass range. Not to say it's not going to be there, but if they exist, it is not in that mass range. The one thing that is kind of interesting about the value of the Higgs mass is that if you look at the Higgs potential, whose vacuum value gives you the Higgs mechanism, that potential, the parameters of that potential vary with scale. And if you go very deep in the ultraviolet, there is a region with that value, for that value of the Higgs mass, where basically the lambda 5/4 coupling goes to 0, which means that you will have a potential without retaining walls, which means it will not be bounded from below. So you have an unstable situation. And that is a mathematical curiosity at the moment, but maybe it's telling us something very deep. That's why that's about as far as I can go.
And in the chat, Roberto Vega commented that presumably this statement about the violating unitarity was under the assumption that the Higgs mass was larger than 1 TeV.
Yeah, right.
Yeah, so the statement was either you discovered a Higgs with low mass or new physics had to show in the form of new resonances. Yeah. And then Pavel Nadolsky noted that in the run-up to the LHC, the concern was more about the naturalness of the standard model radiative contributions than about the unitarity of the standard model. And he points out that that concern about the naturalness of the standard model nonetheless still remains to this day.
Yeah, it still remains, we don't know. But you see, what I'm beginning to think about, except I have nothing really clever to say, is that whenever we look at the vacuum, okay, in the context of the standard model, whatever it is, there's just something weird. I mean, the cosmological constant is weird, okay? I mean, to say the least, right? Okay, the question is that it seems to me that, supersymmetry offers a very beautiful way of triggering electroweak breaking. Okay, but it's still by some squark mass squared becomes negative, is driven in infrared towards being negative, but it's still it's a conventional potential view. Okay, so you're using the Landau views of things, but the question is that it seems that whenever the vacuum is involved, there's something we don't quite understand. I mean, the vacuum, there are lots of vacuum expectation values everywhere. Right. There's something there, and I don't know what it is. I mean, that is, you know, so probably experiment is going to be, it's going to teach us something. But right now, back to the original, the standard model right now does not challenge in an obvious way, any of the fundamentals in the field.
Mm-hmm. All right, Tom, did you have any more to follow up on there?
Oh, I'll give other people a chance.
Okay. Richard, you have a question. Go ahead. You should be able to unmute.
Well, I have a rather silly question. Thank you very much for the stimulating talk. It's really brings forward questions which are deep in my mind. And one of them is the question on time. The physics theory tends to push the energy scale beyond our ability to measure. Is there any reason to believe that time will behave the same way at very high energies as a variable? It's always factorized, right? In our
yeah. Well, yeah, there are other things, right? I mean, when you look at quantum mechanics, I mean, as you said, time is completely different. It's just a parameter that you put there with the Schrödinger equation, yes? I mean, in fact, you don't even need the Schrödinger equation if you're doing quantum information science. You just live in Hilbert space and hoopla, you know? You have fun with it. Yeah, and yet there is special relativity, where all of a sudden time becomes space or space becomes time. They become linked, okay? So, I mean, that again is beyond my pay scale. I mean, right now, I think you just, you know, use it as a, I mean, time by itself may not be important. What is probably important is the sequencing of things, the notion of before and after. But the question of a continuous time, maybe that only occurs when you have a continuous space coming up. But before there was a continuous time, before there was a continuous space, maybe there was still a sequence of events, but it was not necessarily continuous. It could have been discrete. Okay, but I don't know. I mean, you know, those are, as I said, those are things, you know. So before the pandemic, such thoughts, you did it in the shower, okay? While you were taking your shower in the morning, sometimes you thought about such things. With the pandemic, you start thinking about such things a lot more often. Okay, so I plead, you know, it's all the fault of the pandemic.
Richard, did you have anything you wanted to follow up on there? Oh, it looks like you muted again, so I'll assume not unless you say otherwise. All right, any other questions for Pierre? So Pierre, can I ask you a question while we're waiting to see if there's any one last question here? So you mentioned that we still really, on the neutrino side of things, we still need information from experiments. And so, but you also kind of wistfully noted that some of these experiments are likely beyond a single human time horizon at this point. I guess if you could pick any one experiment and say, I want to know the answer from that experiment right now, what would it be? And what would you then do with that answer?
Well, okay. So realistically, okay, we're at the mercy of, you know, well, let's talk about the LHC, for example, okay? And so it could very well be, I mean, this is not a very clean business, but it's looking for new particles, okay? And if basically with new detectors, more computing powers, etc., they have the ability to detect some anomalies. I mean, there are always anomalies in the data, okay? But that's the nature of quantum mechanics too, that basically you can have results all over the place and you don't know. So, but the question that becomes interesting, if they detect some of these anomalies are linked to one another, okay, then of course it becomes interesting. Okay, but if it is, there are two game-changing things, okay, in our future. One, I think, is you know, the detection of proton decay. Now, as I mentioned in one of my slides, hyper K, I didn't mention hyper K, but hyper K will increase the bound by an order of magnitude after many years of running. Okay, that is one thing. And the second one, the second experiment, which will basically tell you whether there's a Majorana mass or not, right, is a neutrino-less double beta decay, which I hardly mentioned. And the neutrino-less double beta decay tells you that, you know, it looks like beta decay, except there are no neutrinos. Okay, and that was proposed in 1935 by well, what's his name? Anyway, 1935, and you know, nowadays the experiments are many orders of magnitude away from possible detection, mostly because of the nuclear physics. It looks like a very complicated, very rare process. But there is one experiment. So those two experiments, you know, are game changers in the sense that they are attacking the global symmetry of the standard model, B minus L. You know, you're going to be able. So it challenges that. But the one thing that is very, very interesting is in the actual measurement of the CP violating phase, the Dirac phase. Okay, and that you know, nowadays there's just a hint for it. Okay, and the effect of this on the overall picture of leptogenesis, what it's called, is just that the mixing angles in a PMNS matrix are large. So even if you have a relatively large angle, okay, but you have to look at its gauge invariant effect, you have to multiply it by the large angles, and therefore it becomes larger. So it has a chance of explaining the number of matter minus antimatter per number of photons, right? Which is the figure of merit of this. So, but let us be modest. Let's first hope that at least we measure the amount of CP violation accurately in the lepton mixing. And there's one more thing I did not talk about, which is the hierarchy. There are two competing hierarchies right now, but that looks to me like it's a normal hierarchy where you have two light neutrinos and a little bit one heavier one, but anyway, that's the way it goes. So, but other than that, there must be surprises. Interaction with dark matter.
Yeah.
I mean, you know, dark matter, I mean, we you know, it's there.
Yeah, well, and there's now this seemingly larger, more open question about what the heck's going on with the mu on G-2, for example. Is that?
Well, that has a number of explanations. There are too many explanations on that one.
Yeah.
Okay, because people have been studying that for 40 years. Okay, saying that this thing, and what was holding up was the contribution of the strong interaction to the process. And now, of course, with lattice simulation, it seems to be converging. So this would be maybe maybe there's a new particle. As far as the LHCb, I don't know. It's only 3 point. I don't know. It doesn't fit very well with anything I know.
Beta SLL, is that what you're referring to?
Yeah.
Yeah. It seems unfortunately trying to put G-2 and beta SLL together gets conflicting explanation.
No, but there are theories to do that, of course. This is what theories do. But you just talk about I don't know. It's also 3.1. I mean, these people did a heroic work going from 2.6 sigma to 3.1.
Yeah.
Okay. I mean, that is truly heroic. I mean, and these guys, the G-2, they could really be on the verge of a discovery, right? Because they're at the level of 4. Yes, 4, yeah. And so, but you know, it's no way to make a business. I mean, to do a business, the real way is to find a particle, for God's sakes.
For example, yeah.
Yeah,
right.
for example. And so finding a particle indirectly is nice, but it's not the full thing. Anyway.
All right. Our last question will come from Durdana, which I think is beautifully symmetric. So Durdana, why don't you go ahead and ask that question you put in the chat, because it is provocative.
Yeah, well, there were times when I was very interested in grand unified theory, and I was always hoping that there will be a new experimental result that will allow us to figure out what is exactly we're doing wrong, that we are struggling to actually have reasonable and practical theory that would unify all 4 fundamental forces. And then we were sort of hoping that the LIGO results will give us some sort of hint to what is going on, to be able to at least bring gravity closer to the other 3. We're still so far off on that. I'm not sure if things with LIGO experiment made things better or worse. So what do you think is the weakest point of the grand unified theory as it stands today, that we are in such a deep mess when it comes to it?
Well, the problem is the number of parameters. I mean, you see, once you have a bigger group, you're increasing the rank, right? I mean, as you go beyond the electron, and the patterns are mathematically beautiful. Okay, and but the question is that the only knowledge we have is the electroweak model, the standard model. So the path between the original grand unified group and this and us is that we have many scales of symmetry breaking, because we have, okay, so we just have the electroweak symmetry breaking, and we don't even understand the mass of the Higgs, how it fits in this. Okay, how come it is immune from radiative corrections? Okay, so you have to multiply this by 4. So for example, if you take SU5, you know SU5 is a rank 4 thing. Okay, so you have to get to SU3 cross SU2 cross U1. So you have to have, in other words, you have to invent, in Landau's language, new order parameters, right, to basically break this more and more. So you're introducing more unknown. And the one thing that we have found that we're not good at all is breaking symmetries. We know how to parameterize it. I mean, Angler and Braut showed us how to do it, and Higgs. Okay, but the question is that it's just a parametrization, and so it's all coming down to the vacuum. And I don't know. So I just taught statistical mechanics, right? So in statistical mechanics, you have the thermodynamics stuff, and you don't have to know thermodynamics. You just do statistical mechanics and you get thermodynamic quantities, okay, et cetera. But if you know, so the question I'm asking, for example, this is pandemic, okay? You're gonna tell me it's stupid. If I do a thermodynamics, the one weird thing about thermodynamics is entropy. The second law is weird. Okay? And the second law tells you that the entropy can only either stay constant or go one way, not both ways. And it's a little bit like time. Time seems to go only one way. So you ask, I mean, this is pandemic, okay? But I mean, it's crazy. The question is that now Boltzmann found the answer. He said there's an underlying thing with Avogadro numbers of stuff in it, okay? And then we can use statistics to understand the going one way in terms of yes, it happens, but the notion of highly unlikely, which is the statistical interpretation. Okay, so right, so the naive thing is that space-time should be, flat space-time. There's something underneath there. We know that it's full of particle-antiparticle pairs, because we know when we calculate our corrections, they work beautifully. Until we get to the goddamn Higgs mass. And this is where, I mean, I'm at the end of my career, right? So I mean, I have tenure. I'm okay. My tenure doesn't depend on these things. But the fact is that it's going to be very difficult to make a, to make a physical breakthrough. Okay. There are times in history where it's very, very hard. I remember German telling me the following stuff. He said, nowadays it's very hard to make a breakthrough. This was in the 90s. Okay. And I said, why? Oh, he said, because Witten hasn't made a breakthrough. He was talking about physics. Okay. Whereas the people who were born in the 1900s and were in their 20s, they were there to make breakthroughs because the breakthrough were happening just like that. Okay, so it is a tremendous amount of luck. And, after all, spectral lines were there for a long, long time. People lived with spectral lines for a long time, and then they got so used to it, they didn't think it was anything interesting. So I don't know. Yeah, it's a difficult time. It's a difficult time. Kip Thorne, when he was asked about the LIGO experiment, he said he was disappointed. And the people asked him why. He said, well, because it's consistent with general relativity. Okay, that's a real theorist talking. I mean, of course, he was delighted, but the question is that the experiment did not show any deviation. And that's a problem. We live under the shadow of Einstein.
Well, I'm not sure if that's hopeful or hopeless.
No. The exploitation is good, but I mean the fact is that usually these people clean up. Mm-hmm. Yeah. But there are times. So anyway.
But
okay.
Yeah, maybe we do live now in a new era of problems that we're taking for granted, but we'll crack the walnut, as it were, on what new physics actually is between dark matter, neutrino mixing, and mass. I mean, I don't know. Perhaps we're living in that spectral lines era again.
Yeah, but no, but oftentimes, read Martin Klein, because what Einstein was very good at was to pick out something that he was unhappy with. Like, for example, in his paper of the electroweak effect, he is very unhappy with the fact that there's the wave nature, which is the whole 19th century way. Okay, and then matter on the other hand, because Einstein studied statistical mechanics like mad, and he says it's all particles. I mean, okay, and yet you have waves, and he puts his finger on it, and by the correspondence of the time, he didn't think necessarily that special relativity was such a big deal, but he thought that putting together wave and particle together.
Yeah.
Okay, and I'm not sure if Planck had not existed, he still would have had the same reasoning, because he never mentioned Planck's in the paper.
That's true.
And it's very interesting. Anyway, so, okay. Now, it is, oh my goodness, it is 6:20.
Yes, I've kept you.
I think I owe it to myself. I have a very old, not very old, 18-year-old malt whiskey. And I think it's a good time to.
Yeah, I think there's no better reason than a good malt whiskey. So, Pierre, on behalf of the department and our community, I really want to thank you for doing this. So, thanks again one more time for this
my pleasure.
Stimulating presentation. Yeah, and no, thank you, Pierre. And you have a wonderful evening.
Yes.
And we'll close out the event. Thanks, everybody, and have a good evening, okay?
Thank you.
All right.
Bye-bye.
Bye-bye.
Bye-bye.